All right, so welcome to the Tuesday session. I want to talk about, well, actually, before I start, let me just thank all the collaborators here on this project, for people at the University of Zurich, as well many members from the FIRE collaboration. And I would also like to point out that the work that I'm presenting today is on the archive, so you can find it there. All right, so we've heard already in a couple of talks that from James Webb, we have now a new kind of information about galaxies at the highest redshift, and there were a couple of interesting things that came out. For instance, we see these, very UV bright galaxies at high redshift. We see very massive galaxies at high redshift, very unexpectedly massive. And also, there is this issue that it appears that the UV luminosity density seems to be elevated, at least compared to expectations based on HST data and also based on some models. So here I show just a collection of models, what they predict how the UV luminosity density for galaxies brighter than -17 evolves as function of redshift. And maybe there are 2 points to make here. The first one is that they kind of all agree, more or less, out to redshift 9 or so, and then as you go to higher redshift, there's a growing diversity. Some fall off much steeper than others. And then if you compare this with observational data, you see that on average, the models seem to unpredict the UV luminosity density, but not all of them. Okay, so maybe that should also be kept in mind. We already heard yesterday about several potential explanations for this difference between, let's say, the median of the models and the observations. For instance, that the star formation maybe is more efficient at higher redshift. Maybe there's something to do with dispersity star formation, or maybe also with the mapping between the UV luminosity and the star formation. So what I'm going to talk now is to look at this from a theoretical/numerical perspective. So I'm going to study the UV luminosity density in Firebox HR. All right, so what is Firebox HR? Let me step back first. So this is part of the Feedback in Cosmological Environments project, FIRE. And to understand Firebox HR, you first need to understand what Firebox is. So Firebox is a cosmological volume simulation with higher 2 physics. It's a relatively small box, only 22 megaparsecs or so on the side, has about 1 billion gas particles in there, mass resolution that is at the lower end of zoom-ins, and it's run to redshift 0, and you can see where it falls into this, let's say, volume versus mass resolution plot in the top right side of this slide. Firebox HR is exactly the same volume, but at 8 times better mass resolution. So it really has the mass resolution of state-of-the-art zoom-in simulations of, let's say, Milky Way. But of course, because of the much higher computational demand, it's only run to about redshift 6. It's run with the standard Fire 2 physics, so there's no changes. Okay, it's really exactly the same as Firebox, just with higher mass resolution, and also the same as other Fire 2 lumen simulations. So this means, for instance, that the cooling is down to 10 Kelvin. Stars only form in dense, self-gravitating molecular gas. There are various channels of stellar feedback, but there's no agent feedback in the simulation. Okay, so that's the simulation that I'm going to talk about. So this Firebox HR simulation. And maybe just a brief slide about the analysis. So it's pretty standard. So we run Halo Finder on it. So we extract all the galaxies. All the properties are measured within spherical apertures. And then we calculate UV luminosities, right? So based on stellar synthesis modeling. And for the more massive and therefore dusty galaxies, we use a dust radius transfer with SCIRT. Okay, so let's take a look at the UV luminosity function in Firebox HR. So if you look, let's say between redshift 6 and 10, we find generally good agreement with observations. So here on this plot all the colored lines of Firebox HR. So the colored lines and symbols are Firebox HR. All the black lines and symbols are observations. So the lines essentially are fitted UV luminosity functions. So the thick lines is where they are measured. The thin portions of the lines are just extrapolations to guide the eye. Okay, so they are actual measurements. So typically, for instance, that UV luminosity function is only measured down to minus whatever 17 or 18 at redshift 10, but at redshift 6 we can go to minus 15. All right, so you see kind of interestingly that at redshift 10 it looks more or less like a pure Schechter function, the UV luminosity function in Firebox HR, but as you go to lower redshift, you can clearly see that there's a turnover at faint luminosities, and we interpret this as a result of ionization. So if you go to higher redshift, again, you have a very steep faint end. Where there's overlap with observations, we tend to agree. You know, because of the small box size of the simulations, we don't have very bright galaxies in the simulation, in the volume there. Okay. So now let's see how the UV luminosity density looks like in Firebox HR. So let me plot this, and it looks like. Okay, so we are essentially in broad agreement with the observational data out to redshift 14. All right, so let's try to understand what's going on here. Why does it work in Firebox? Why does Firebox give you this, let's say, elevated UV luminosity density? So the first thing that I want to say is that maybe the first question to ask, which galaxies are actually responsible for most of the UV luminosity density in the universe? Okay, and here again, I mean most of the UV luminosity density of galaxies brighter than a certain cutoff, and you know, for convention, the cutoff here is minus 17. So, what I show here is just the UV luminosity that contains half of the UV luminosity density in galaxies brighter than minus 17. And you can see that this magnitude is about minus 18 to minus 18.5 for, let's say, between redshift 7. So it's clear that much of or most of the UV luminosity density is not in bright galaxies. Okay, it's not really surprising. Not in bright galaxies, it's in moderately faint galaxies. So really what happens at the bright end, whether we have an overabundance of bright galaxies there or not, has really almost no effect on the cosmic UV luminosity density, right? So really these are two different kind of problems. We can solve this one, for instance, and yet not solve the issue with the bright end, or we can solve the bright end and still have problems at producing the UV luminosity. So these are really two separate problems. Maybe they have the same solution in the end, but in principle they could be separate. I should also mention that the galaxies that have this kind of magnitude, they tend to sit in halos also that are also moderately massive, so between 10 to the 9 and 10 to the 11 at redshift 6 to 50. All right, so star formation efficiency is the next thing to look at. So we calculate this directly in Firebox in two different ways. The first one is, let's say, based on the star formation rate, which is the star formation rate divided by the halo growth rate. That's the one on the left. And then the one on the right, which is more directly linked to the UV luminosity density, is essentially the UV luminosity, the best attenuated one, divided by the halo growth rate times conversion factor. And they have a very similar behavior. So in particular, they are both essentially redshift independent over this important halo mass range, so between 10 to the 9 and 10 to the 11. So in some sense, they are constant star formation efficiency. Constant means non-evolving with redshift, but they're also constant in a different sense, because they're also very weakly halo mass dependent. So the slope on the left is about 0.37, and the slope on the right is about 0. Okay, so there's also only a very weak halo mass dependence. And in fact, if you compare the slope of the star formation efficiency that is predicted here from the simulation with other models, you see that in essentially all other models, the slope is steep. So that's really a distinguishing feature of what FIRE 2 predicts. All right, so now can we understand the scaling? I have a slide on this. I don't know how much time I have. I probably don't have much time. But let me give you a somewhat speculative argument as to why we get this low redshift, let's say weak redshift dependence or absent redshift dependence in weak halo mass scale. So the idea is that the star formation rate is proportional to so 1 over the mass loading factor times the halo mass divided by the peak. Okay, and I'm also talking here again on low mass galaxies where typically the mass loading factor is larger than 1. Now, how can you motivate this? Well, you can go to say the gas regulator model, and you can plug it in, and then the only thing, essentially what you have to assume here is that the gas inflow rate into galaxies is essentially proportional to the halo mass divided by the peak. Okay, and then you end up with this. The next ingredient is that you have to know how the mass loading factor scales with halo mass. And this we know because we have measured this in FIRE 2 simulations. At high redshift, it scales essentially, so we essentially have energy-driven outflows, so the mass loading factor scales like 1 over the circular velocity of the halo squared. And then you combine all these things together, you find that the star formation rate scales proportional to 1 plus c to the 5's half times m halo to the 5/3. And the star formation efficiency, if you, for instance, use this parameterization of the halo growth rate, just for illustrations, they are more, let's say, more accurate estimates out there, but for this purpose, it's good enough. So if you now divide this by the halo growth rate, you see that the star formation efficiency should scale about to the halo mass of a power of about half, and should essentially be redshift. Okay, and that's essentially what we see in this situation. All right, so now we can combine all these kind of things together. We can take the halo mass function, the halo accretion rate, and the star formation efficiency. The latter we measure, as I said, directly from the simulation, and fit it, and then we can use it in parameterized form. And then we combine this to get an estimate for what the luminosity density is. And that's what we find. Okay, so that is now for the prediction of a theoretical model, right? It's pure theoretical because all the ingredients here are based on theory. There's no observational constraints that are used here to fix anything. We find, so just look at this thicker blue line here, that we match the observations again, and we of course also match the simulations. Okay, so this model seems to work well. What we, for instance, see here from this model is that it's not a single power law. Okay, so the UV luminosity density doesn't decline as a single power law, but rather it's kind of a gradual decline that gets steeper and steeper as you go to higher and higher redshift. And also, if you, let's say, integrate or lower the magnitude limits to, let's say, -12, you find that that you're not able to kind of reproduce an edge-like signal. All right, so now there maybe comes to the question, so what drives the UV luminosity density at high redshift? So let's look again at the star formation efficiency plot, and let's now overplot the following. So essentially what I'm doing now is I show you the contribution of different halo masses to the UV luminosity density. Okay, at different redshift. So the different colored lines correspond to different redshift. So let's say at redshift 6, you can see that so 50% of the UV luminosity density essentially comes from halos that have halo mass of around 10 to the 5. As you go to redshift 15, so 50% of the UV luminosity density comes from halos with halo masses of maybe uh, 10 to the 9.3 or so. Okay, so this is what we have. Now let's do the following. Let's make our slope of the star formation efficiency halo mass a little bit steeper, right? So I mentioned at the beginning that our slope that we get from pi or 2 is particularly flat. Let's make it steeper. Let's say like that. And what now happens is that, of course, we have a steeper slope, and therefore the halo mass that produces most of the luminosity density shifts a bit to the right as you go to the right. But that means, right, because the halo mass function evolves very, very steeply with redshift, that you have fewer objects at higher redshift that contribute to the UV luminosity. Therefore, you end up with a lower UV luminosity. So, back and forth. So let me just give you the conclusion here, and that is if you have a shallower slope of the star formation efficiency halo mass relation, you therefore have an increased contribution of the more numerous galaxies at higher redshift, and therefore this boosts your UV luminosity. How am I doing? Okay, good. All right, good. So let's move on to some implications then. Okay, so we have now, I think, explained, or I propose this as explanation, why the UV luminosity density is higher than we perhaps expected at high redshift. Now let's see. And now I also showed you this kind of theoretical model, right? So that's just based on the star formation efficiency that we take from simulation. Let's now see what an implication of this is for the ionization history. Now, in the simulation, I don't know what the escape fraction is, and so it's a free parameter. In fact, it's not the escape fraction that's a free parameter, but the escape fraction times the ionization or the ionizing photon production efficiency is the free parameter. So that I keep as a free parameter, and I constrain it by choosing it such that I produce the optical depth, the Planck optical depth. And if I do this, for instance, if I choose it such that I reproduce exactly the Planck value here, then you can see the ionization history that then follows is the blue line, which more or less agrees with the observations that we have. However, it's actually better to lower this a little bit. So if you, for instance, kind of reproduce this optical depth here, just 1 sigma below Planck, then you essentially then you follow this track, and this seems to also agree quite nicely with the observation. So it seems like essentially a value in between here is the one that is most consistent with the observational data. And this, if you look at what this corresponds to in terms of ionization efficiency, escape fraction product, it's about 24.5 to 24.7, and now of course you can play games and say, okay, let's say for instance, if the escape fraction is, let's say, 20%, as we found in prior simulations earlier, then this would imply that the ionizing photon production efficiency is about 25.2 centimeters. Okay, so let me bring up my summary slide. Okay, so unreduced firebox HR. Okay, so essentially a cosmological volume simulation with prior to physics at the resolution of zoom-in simulations, but it stops at high redshift. The simulations results are more or less in good agreement with the UV luminosity functions between redshift 6 and 15, and also with the UV luminosity density. And we find that the star formation efficiency is non-evolving, so we have a constant star formation efficiency model, but we have a relatively shallow or weak halo mass dependence. And as I tried to argue to you, this weak halo mass dependence is the main reason that we find this somewhat elevated UV luminosity density. In particular, the scatter of the star formation efficiency halo mass relation is not responsible for the elevated UV luminosity. Okay, so in fact, you can actually show that the scatter. I mean, if you have no UV the magnitude limit, then the scatter also plays zero role. And if you have a magnitude limit, then the scatter plays a small role, but it's really not. At least in our case, it's not responsible. Okay, thank you very much.
Thank you. Are there any questions?
Very nice work, Robert, and very interesting way of understanding the UV luminosity evolution. One thing that you didn't discuss, though, is the comparison between original Firebox, for which you're also the lead author, and your new one. What are the main changes?
Yeah, so the main changes, as I said, is there's no main change. It's really just higher resolution. 8 times, it's just 8 times better mass resolution. Otherwise, it's identical. Yeah, we didn't look at this. Yeah. Yeah, that's an interesting question. Since I have the higher resolution, I'm not sure this it's a super interesting question. Yes. Yeah. So it might have been good enough. I mean, so one of the reasons why it's nice to go to this kind of resolution is because that is kind of like, say, the standard resolution that we use for Fire 2, so for all the zoom-ins. And this is kind of means that it's really fair to compare what we do here with and link it to the Redshift 0 stuff, right? In the other Firebox, let's say in the original Firebox at the low resolution, so there definitely are some resolution effects. So we showed this there explicitly. In particular, in halos of 10 to the 11, you get a somewhat higher like stellar mass, and therefore also higher star formation efficiency. I would gather, I would guess. So yeah. So there will be, in detail, there will be some differences in predictions of the model, but this resolution here is really nice because it is the one we use for the
So this is probably just a conceptual problem on my end. So you're not finding that there's a strong redshift trend to SFE, but one of the impressive things about Fire is that it's capable of matching these very high SFE galaxies in the early universe. So how do those two things interplay with one another? Like, why aren't we also getting super high SFE galaxies in the late universe?
Okay. Yeah. So that's a very good question. Now, what I talked about, and I think it was very clear, but it's really important to stress, this is only for halos from 10 to the 9, 10 to the 11, and I don't know exactly what happens at the more luminous or more massive halos. So it's very well possible that, I mean, we have run, let's say, zoom-ins of more massive halos showing that the star formation efficiency is very high. So it's very likely that the star formation efficiency will start to go up as you go to the more massive halos, but that's not something that I can answer based on this. Yeah. Okay. Yeah. So there's more talks about where you can make money out of it. So okay. So let me just be 100% clear again. So scatter has a huge impact on the luminous end of the luminosity function, right? There's no question about this, right? Just because they're very rare objects, so you scatter more likely to the bright than to the faint. But what I'm talking about here is if you're integrating the UV luminosity function up to certain limits, and so arguing in the beginning, the bright end has no impact on this integration limit. So the scatter there here for this question, the scatter matters not. But yeah, for the number density of UV bright objects, it's a completely different ballgame.
So yeah, I was also surprised that since you don't test the high mass end, how can you be sure that it's the low mass and that dominates? But you mostly
showed this here. Here we go.
Yeah.
So if you just take a UV luminosity function and you integrate it, you see that there's not much luminosity coming from the bright one.
And how do you know you have converged on your code? Because you say, now I have a higher resolution, I get a different result. Now, when will it stop?
That's not what I said. So okay. So this analysis I've only done for Firebox HR. I have not done it for lower resolution rerun of it. So I don't 100% know. I just know that we looked when so I compared Firebox, the lower resolution one, at low redshift with zoom-ins, which have the same resolution as this simulation. Right? That's why we picked this resolution. And there we find some differences with those solutions. So as you go lower resolution, we see some differences. Meaning that galaxies are slightly more massive, things like this. So I'm not claiming that that fire is strictly converged. I don't think anyone actually claims this. But I think the point is that you need to reach a certain resolution in order to essentially so that you have essential results that are comparable.
Okay. We will have the last question while the next speaker can come here and prepare.
So this is just following up a little bit on Joel's point. I mean, I do think one thing you could do with Firebox HR is make predictions about what's happening at the faint end of the luminosity functions. And you didn't emphasize it, but there is a prediction that they're rolling off. After reionization, they flatten.
Yes.
I think that's a pretty robust prediction. I think if that doesn't happen, you overpopulate the satellite population of the Milky Way. So you're sort of solving the missing satellites problem in this way, and it's very connected. So in principle, it's going to be very exciting to look for those rollovers in real data, because it'll sort of tie this sort of near field to far field expectations together.
Let's thank the speaker again.